In this subsection, I want to focus a bit more in detail about the dangers and consequences that you would face when you encounter a release of either a gas hydrogen or a liquid hydrogen. And I want to quickly mention about the Australian standard that has recently been published in support to the you know rising increase in support to the rising interest of hydrogen research as well as utilization recently in Australia. So a couple of key points that you have to consider when you assessing an accidental release of gaseous hydrogen. You need to kind of understand the characteristic of the release, the pressure and the size of the release, whether that release is done in a free field or in confined space. So we know before that you have a confined space, then the expansion or the volume expansion would cause a very problematic to the structure that hold it. So you have to also be aware of the potential ignition source, whether there's some potential ignition source available around or there's not. And if there is an ignition that can be, in the surrounding of the releasing, then would it cause an immediate ignition or would it cause a delay ignition? So all of these points are the things that you need to be consider when you are facing with a release of gaseous hydrogen. All right, so if the hydrogen released in a free field, right, and if it released with an immediate ignition, meaning that the hydrogen it's ignited immediately after it's been released, then what you have is just a jet fire, and the hydrogen jet fire is going to keep going on and maintain as long as the source not shut off. And we know from the chemical property of hydrogen that because of the low radiant heat, the hydrogen flame or hydrogen fire would produce less heat compared to other fuel. So again, you have to be careful because you might be in the flame before you can even feel it. However, if you have the gaseous hydrogen released in free field, but you have what we call a delay ignition, then what happened with that? You would have a flammable cloud being formed before that ignition actually starts, and because you have this flammable cloud already being formed, then it might as well bring it to the detonation level of the hydrogen. So when that happens, would cause an overpressure effect that carry the energy that can hurt people and other building or installation in the surrounding. And of course, the level of congestion around that site is also an escalating factor. And I just have to be careful with this DDT phenomenon, because it would lead to a very severe consequence to structure if you have such confined or obstructed situation associated with this delay ignition. If the gaseous hydrogen released in a confined space, then the pressure picking phenomenon can happen. And this is not just happen specifically for hydrogen. In fact, it can happen to any gas that is lighter than air, because it can cause the overpressure that exceeding the enclosure or the structural strength limit of that vessel, to a point where the enclosure or the vessel can be strongly damaged up to a point of total destruction. So whether it could lead to that total destruction, depending on a number of factors, depending on the release flow rate, is that a high release, depend on the volume of your enclosure and the size of the vent that you put in place. So when you release in the confined space, you have to be aware of the hydrogen buildup, right? So these are the images that I took from the High Responder project report, where they simulate the release of hydrogen in confined space with different ventilation scenario. If you don't have any ventilation, then hydrogen which can be quickly mixed and stratified in that room. But even if you have natural ventilation, you need to be strategic on where you put this ventilation port. Ideally, you want to have two ventilation ports, one at the bottom vent at the figure on the middle here, so that the air can be sucked into the confined area and carrying the hydrogen to the top of the enclosed area. And you would also want to use a mechanical ventilation if you calculate that, okay, the rate of air coming in to your system compared to the rate of hydrogen being released is not sufficient to bring it down to a level that is safe for human, like 19 volumetric percentage, or it's not safe enough or below the lower flammable limit. Then you have to apply a mechanical ventilation to force the extraction of hydrogen away from this enclosure area. In a confined space, if you unfortunately encounter with an explosion, then you should be aware that if you have a appropriate or dedicated venting mechanism in place, that could have to mitigate the effect or the undesired effect of an explosion in that confined space. So an example you can see in the figure here, right? Again, from this is the picture I took from the HiCR project, where they conduct experiment in 3 different scenarios in a container. The top set of figure here where they actually let the hydrogen ignite with the container door closed. The second set of experiment is that they have the hydrogen explosion when the door open, and the third option or the third set of images here is when they have a dedicated venting mechanism in place. And the first two top set of figure here showing that if you don't have an appropriate venting to have release the pressure causing by explosion, then the structure of the container could be completely destroyed when you get the door closed, or if you have some deform to your structure. But the best case scenario is that you should have the venting mechanism at the bottom figure here, which allow to mitigate any adverse effect coming from the explosion with respect to the structure of the container. Another way that hydrogen can be released is to a burst of a pressurized vessel. So unlike the other explosion that I've just been mentioning, this is a physical explosion. It also leads to a rapid expansion of gaseous hydrogen, but it's not as high as liquid hydrogen expansion. It's still high, but not that high. The expansion ratio is from 1 to 240 when the gaseous hydrogen is at 250 bar at 1 atmospheric pressure. And when a physical explosion, it would generate overpressure wave, similar to a chemical explosion, and also a potential fragment coming from that pressure vessel as well. So a couple of reasons that can lead to that burst of pressurized vessel. One with that normal working condition. It could be because of degradation with time of the pressure volume or the mechanical impact on the pressurized volume as well, or at bursting rupture pressure, or because of overfilling, or you don't have adequate pressure relief, or you have other reason because of internal explosion or in fire crashing. So to detect hydrogen release, the couple of options that you can use to put in place if you want to detect gaseous hydrogen release, then you can have explosimeter, you can have combustible detector, or even you can have acoustic detector to show you where the localization of can happen on a screen, or you can have a chemochromic tape or other chemochromic media wrapping around a connection to have you detect with hydrogen. But for example, like probably nothing beats the ease of using just soapy water to detect the leak of hydrogen. If you want to detect the hydrogen flame, then the utilization of thermal imaging cameras is a must. So that was the couple options for portable detection device. You can also use the fixed detection device as well. So also divided into either gas or flame detection. For gas detection, you can use explosimeter or acoustic detector. For flame detection, either UV or infrared detector or multi-IR detector can be used. All right, so with respect to the hazards caused by liquid hydrogen release, I just want to use the result. I want to present the result of the research work conducted by the Boston Health and Safety Laboratory in UK that they've been conducted over the last 10 years, where they're trying to release liquid hydrogen from a 2.5 hydrogen tank to a 1-inch diameter hose, so that the liquid hydrogen release would be in the range of 60 liters per minute. And they, for this unignited release, meaning that they just release the liquid hydrogen to the field without even attempting to burn it or to ignite it. They look at the visual inspection, look at the temperature of the concrete where the hydrogen, liquid hydrogen is released, and also the concentration of hydrogen, as a function of distance and height from the release point. And the outcome that they got with that, they can detect a visual hydrogen cloud up to 8-meter height from the point of release, and they observed the formation of the liquid pool, which basically the hydrogen droplet that is falling onto the ground and forming that pool, and this is referred to as the rainout phenomenon. And they also observed the formation of solid deposit close to the release point. They hypothesized that solid deposit is a mixture of solid nitrogen and oxygen, right, condensed from the air and trap some of the liquid hydrogen within the matrix. They try to ignite this solid, so it is ignitable, but it is not explosive. A couple of outcomes that they record the temperature of the concrete on the surface and at the depth down to 30 millimeter, and they recognize that the release of liquid hydrogen can cool the surface down significantly. It can go down to 16 Kelvin, so it's really, really low on the surface. And even if you go down to 10, 20, 30 meter, at the lowest point here on the 30 millimeter depth is also at the range of 150 Kelvin. About the concentration of hydrogen, you can see that the red line here, we have number 4, which is the lower flammable liquid of hydrogen, and the green line here, which stands for the stoichiometric concentration of hydrogen and air. You can see that the flammable level of or flammable range of hydrogen can be kept up to a distance of 5.5 or 6, and up to the height of more than 2.5 meter. And this is only the data they have when the wind favor the the migration of hydrogen to the detector. But still, what I mean is that you have a very wide area that is containing hydrogen under its flammable range, flammability range that we mentioned before. Well, sorry. So a couple of years later, they're trying to, doing the exact same kind of test, but this time they're trying to record the ignition of this release as well. So, same condition with 2.5 ton hydrogen tank to a 60-liter minute release rate. They use a 1 kilojoule chemical igniter trying to ignite the vapor, and they try to measure the heat flux and compare that heat flux value to a no harm criteria or criterion at 1.6 kilowatt per square meter level. This level meaning that you can be exposed to this heat flux regardless of how much time you in that kind of exposure, and you would feel it would be no harm to you to people. They also record the overpressure effect and also the thermal dose safety distance, right? Just to quantify, okay, how far should you be away from the release point? And they found out that if they try to ignite the cloud, after you let the cloud build up and let the deposit build up, then it's actually quite difficult to ignite the vapor. And the two main reasons for that is because you either have under or over-rich concentration of hydrogen at the point of the igniter, or simply because you have a quenching effect created by this water vapor that from the cold hydrogen. So they try to change the strategy and then ignite the liquid hydrogen, shortly after it's been released, and does not allow any liquid pool or solid deposit to form, and the ignition was successful, and they can ignite the liquid hydrogen right after it's been released. And from such ignition, they recorded 4 separate regions. The first one is an initial deflagration of the cloud back to the source, or what they refer to as a burn back, and then a possible secondary explosion. The reason they put possible here is that for some case they actually don't have that secondary explosion, but in some case that they do, and they measure the energy or estimate the energy that can be released from this kind of explosion and try to put a number on it, and the energy release is about 18 megajoule, or equivalent to about 4 kilograms of TNT explosive, with an estimated release of 150 grams of hydrogen being released to the field. With respect to the Z5 phase here at the back end, it is dependent on the wind condition. So when the wind conditions were minimal, less than 0.6 meter per second, then that jet fire was buoyancy driven, as in it's going to go up, vertically. But when you have a strong wind, so in this case they using any wind speed that higher than 0.6 meter per second, then your jet fire is going to be a momentum dominant jet fire rather than a buoyancy driven jet fire. The last outcome of this project was that they was able to quantify the distance, or the minimum separate distance for this 60 liter per minute spin. Just be aware that this number that they quote here is only valid for 60 liter per minute spin only. You cannot just interpolate or extrapolate this number. And what I mean is that if you want to be safe from the initial cloud deflagration, then you stay away at a distance, further than 11 meter. If you want to be safe from the secondary explosion, then you should stay at a distance of 11.3 meter. To avoid the jet fire phenomenon, doesn't matter whether it's low wind and high wind, then you should stay at the distance of 13.7 meter. So I think this is a really cool project and have a very practical outcome. If you're interested in knowing more about that, I would suggest to follow more on the Press High project, which was completed recently, and they have a document entitled Handbook of Hydrogen Safety, a chapter on liquid hydrogen safety. I provide a link here just in case you want to follow it and to read more about the outcomes. Because of the release or the storage of the infrastructure associated with the storage of liquid hydrogen is normally in the free field. The release of liquid hydrogen in the confined space hasn't been studied much. And it's normally kind of accepted that when it's released, then you would have liquid hydrogen being released with a large expansion ratio. It form a deposit and the hydrogen pool as well, but they would eventually be released at cold gaseous hydrogen. So what I mean is that if you ever come to a point where you have liquid hydrogen spilling into a confined space, then in addition to large expansion ratio, it should be treated as similar to not treated, but it should have the similar consequence to gaseous hydrogen released in a confined space. And as a result, not a lot of work has been done on the release of liquid hydrogen in a confined space. Before concluding this section, I just want to touch base to quickly mention about the standard that has been using or just recently been published in Australia. So in 2021, the Australian standard from the ME-093 Hydrogen Technology Committee, which they aim to develop the Australian standard, working with other Australian Standard Committee to consider and adopt international standard with respect to hydrogen. And this standard has been established with the aim of consider the whole entire hydrogen value chain to with respect to health, safety, and environment. And they consider 5 working groups as showing on the right side. Again, I give a link down here in my slide if you want to follow more on this work. Feel free to click on this link and check this out. The standards are being updated and are being uploaded onto the standard website. So make sure you keep yourself updated on these standards as they becoming available. So in this session, I just want to briefly mention about the hydrogen safety research at the University of Newcastle in Australia. Before we dive into what we're doing, I just want to quickly mention about explosion, chemical explosion, and the DDT research, our research group. So explosions. So the definition of explosion is given here, but basically an explosion can result from the rapid release of energy, right? So the release of energy is going to be had to be really sudden to a point where it causes an accumulation of energy at the site of the explosion, right? So when you have that energy being accumulated, it had to be dissipated one way or another. It can be in the form of pressure wave, projectile, thermal radiation, or even a positive energy. And the damage from such explosion is normally caused by this, energy dissipation. So if the explosion occurs in the gas, then the energy would cause the gas to expand rapidly. And what it does is it pushes back the surrounding gas, and it would form a pressure wave that's going to move, rapidly outward from the plot source. So because the pressure wave carries energy with it, that energy would cause damage to the surrounding as well. So there's a couple of definitions that I leave it up here. I won't go into detail with, but just want to leave it here just in case you want to follow more about a blast wave, a shock wave, and the peak over pressure of an explosion. An explosion can be a nuclear explosion, it can be a physical explosion, it can be a chemical explosion. So in my talk today, I'm just going to focus more on chemical explosion. It's basically involve rapid chemical reaction. You're going to form large volume, high pressure, and high pressure in a very short time. You're going to, release a large amount of heat in the form of amount of energy in the form of heat, and the damage that's coming from this chemical explosion is going to be depending on whether that explosion is coming from a deflagration or detonation. So what are these two? We've been hearing about deflagration and detonation a couple of times in my presentation. So basically just keep in mind that deflagration is a subsonic wave supported by a chemical reaction. Subsonic meaning that the reaction front of this phenomenon is going to be traveling, at the speed that below the sonic velocity, and the speed of the sound traveling in medium depending on the medium composition. For example, if the sound, the speed of sound traveling in a dry air is about 340 to 350 meters per second, but if that sound is going to be travel in, say, a stoichiometric of hydrogen in a mixture, then its speed is going to be increased to 404 meters per second, because the speed is travel depending on the elasticity and the density of the medium. The elasticity of hydrogen and kind of the same, but because hydrogen is significantly lighter than air, like about 14 times lighter than air, then the sound can travel at a faster speed in a hydrogen air mixture compared to just a dry air. Anyway, so what I mean is that when you have a deflagration, the reaction front of your chemical would moving at a sonic velocity, whereas your pressure front would move away from the reaction at the speed of sound. And what I mean is that the pressure front would move away, whereas the reaction front is going to try to catch up with it. So, the characteristic of this pressure front under deflagration is that it had the duration of many milliseconds. It's flat. It doesn't have any abrupt shock front. It has a very low maximum pressure, normally just 1 to 2 atmospheric pressure. However, when it comes to detonation, it is a completely different story. So detonation is a supersonic wave supported by a chemical reaction. So in this case, your reaction front is going to be moving at a speed higher than the sonic velocity, and it's going to carry or driving the subfront like right in front of it. And the characteristic of this subfront would be that it have a very short duration, the range of less than 1 millisecond. It's characterized by a very sharp and abrupt pressure rise, and have a maximum pressure of higher than 10 atmospheric pressure. So between deflagration and detonation can certainly cause much more catastrophic consequence than deflagration. But a deflagration can evolve into a detonation if you keep offering the energy to that pressure wave. So this is a very complex process, and what I call is a deflagration to detonation transition. It's normally commonly happen in pipes, and it doesn't happen. It's unlikely to happen in vessel or in open space scenario where you store your hydrogen. So the focus on DDT study on the transition of deflagration to detonation is to understand how and when and where DDT would occur. Once you have that knowledge, you would be able to build up safety mechanism to avoid the unwanted and catastrophic consequence caused by detonation. And it takes a long way to get there, but basically this is what we've been focusing at the University of Newcastle. Our goal is to conduct research on the safety aspect of hydrogen, but have a focus on the DDT phenomenon. And the general goal is to acquire the data to have the design of suitable mitigation and alarm system to avoid, this transition phenomenon to happen. And we know that before that hydrogen is going to travel really fast. So you need to conduct experiment in a large scale and have enough space or distance to allow the transition to happen. So that's why our experimental works can be conducted in a large scale detonation tube at our facility. This have a 30-meter long propagation tube with a 0.5 meter diameter, equipped with a number of 50 millijoule chemical igniter to have the ignition of the gas mixture. And we're going to try to look at the temperature and pressure, as well as the flame intensity, profile, and velocity of this hydrogen and oxygen and air mixture, and to understand how the pressure wave profile and velocity would form when the DDT of hydrogen and air or oxygen would happen. All right, so in the conclusion part here, I just want to have a very quick concluding remark with respect to hydrogen property, you know, mentioning some notable projects that have been using the data, the conclusion to build up this presentation, and the couple of reference that I would suggest you to have a look at it if you are interested into hydrogen safety. So the concluding remark that I want to emphasize that, from a safety point of view, hydrogen is not more or less dangerous than other fuels. I think the right term here should say that hydrogen is different compared to other fuels. It has a unique set of physical property and combustion characteristics. And to name a few, for example, it has very small atom and molecule, low density, high flow rate, high diffusion rate when you compare to other gas. It also has wider range of flammability, fast flame propagation, but with a proper knowledge or understanding of the design and the engineering, and if you handle the hydrogen in a careful and professional way, you'll be able to use hydrogen in a safe manner, and can prevent any incident and accident that can happen, or even put in place measures to mitigate or control the incident should it happen. So yeah, my concluding remarks that is not more or less dangerous compared to other fuel. Just need to understand its property well enough to be able to use safely. So a couple of projects that I want to mention that have been dedicated to the safe utilization of hydrogen. And I provide a link here, a very short description of what they are. Feel free to, I recommend you to follow their website, have a look at their work, because that would be a very good starting point if you want to understand more or to know more about hydrogen safety. So we'll start with the project HySafe, which duration between 2005 and 2007, later on followed by project HyFight, which then later on evolved into the HyResponse, which completed in 2015. Project HyCI as well, which focusing on the standardization of vent site equipment, which completed in 2018. Press-in project, Press-High project, with focusing on the use of cryogenic liquid hydrogen, which was completed last year. Shift project, with focusing on the handling and use of hydrogen, which is due to complete this year, and also the International Association for Hydrogen Safety is something that I would recommend you to have a look. The last two notable projects would be HyResponder, which also due to complete later this year, and also the Hydrogen Tool, which is a database of hydrogen safety and handling that you can check to see all the hydrogen incident that they try to record all the hydrogen incident accident that happened. So this is a very good website to follow as well. With respect to reference, the couple of references that I've been using for my presentation, but I would highly recommend you to have a look at the book published by Professor Monkhoff, The Fundamentals of Hydrogen Safety Engineering, the two-part to the book. They are freely downloaded online. If you're in Australia, then make sure you have a look at the basic consideration for the safety of hydrogen system, which is published by the Australian Standard late last year. And if you're interested in other safety implication, I would suggest to check a couple of other books that I listed here as well. All right, so I guess that's it from my side. So yeah, just want to say thank you for hanging around and for being here. And if you have any questions, feel free to contact me using the email that in the slide. And I hope that I will hear back from you soon. And thank you very much for stay with me to the end of the presentation. So thank you. Bye.